Any questions?
Hocam, şeyi tamamlayamadım. Gauss'un çeşitlerine bakarken elektrik alanının diskontinüs oluşundan bahsettik. Orada tam anlayamadım. Yani. Videosunda koyamadım. Tekniklerden dolayı. Orayı tekrar edip
Okay.
gördüğünüz durumda ödevde
Let's do an example that we already know. We had studied this infinite parallel plates. Let's say the charge density in the above plate is plus sigma. In the lower plate, it is minus sigma. We know that the electric field out of the plates, it is equal to 0. And in between the plates, it is uniform, pointing in this direction. And it is given by, let's say this is the z-axis. Electric field is sigma over epsilon 0 in the minus z direction. This is our electric field in between. Now, what we had discussed when we were discussing the Gauss law, where we had imagined such surfaces, such Gauss surfaces, such that one side of the cylinder is on one side of our surface charge density, and the other side of the cylinder is on the other side of the charge density. And we apply the Gauss law. Now, the result, our final result was the electric field at the top minus the electric field at the bottom. Well, let's look at this example. Now, let's apply it at this point. And let's choose the direction of our surface to be in that direction. Okay? That is the n hat is the z hat direction. What is the electric field at the top of this surface, at the above side of the surface? Above meaning this n vector points below the surface to above the surface. That is how we define below and above surfaces, or the top or the bottom of the surface. So if you take this surface has two sides. One of them we call below, the other one we call the above or bottom and top. And this n vector points from bottom to top. So what is the electric field at the top of this point P? What's the electric field? The top of that point is this region over here. What is the electric field in that region? Yes? Is it this one, or this one?
Zero.
It is 0. So for this surface, since we are taking the n vector to be in the z direction, this is the top surface. This is the bottom surface. If you approach our surface from the top, electric field is everywhere 0, including at the top of the surface. What is the electric field at the bottom of the surface? That is, you approach this point from the bottom of the plane. The bottom is below the plane. Minus sigma over epsilon 0 z hat. So this difference in the electric field at this surface is equal to sigma over epsilon 0 in the z direction. Well, sigma over epsilon 0 in the z direction is nothing but sigma over epsilon 0 in the n direction. This is our general result. Now, this result, although here we applied it for an infinite parallel plate, in fact, it is correct in general. Whatever your surface is, it can be curved or it can have uniform, non-uniform charge density. This is always the case at the point R. This is always the correct relation. So you imagine a surface It can be any surface. Of course, first you have to determine this surface. For example, in question 4, as you said, you were supposed to use this relation to determine the surface charge density. But to use this relation, first you have to identify the surface across which the electric field is not continuous. So first you identify the surface at which the electric field is, changes discontinuously. And then if there is such a surface, on that surface there is a surface charge density, which you can determine by using this relation. So you just take, for example, this point over here. If this is your chosen n vector, that means this side is the top of the surface, this is the bottom of the surface. So if you approach this point R from the top, if you take the limit, then you obtain an electric field, which is what I denote by E top. If you approach the same point from this limit, then you obtain another electric field, which I call the E bottom. These two limits, although they are the electric field at this point on the surface, these two limits can be different. Well, if the limits are different, it just tells us that there is a surface charge density at this point. Let's do a simple example. Let's look at this electric field. It is 1 over 4 pi epsilon 0, q over r squared in the r hat direction. Let me multiply it with r minus r. Well, this is basically 1 over 4 pi epsilon 0, q over r squared in the radial direction if r is larger than capital R, and it is 0 if r is less than capital R. To find the charge density that is creating this electric field, let's take its divergence. Well, we had already seen that basically this is the electric field of a point charge. So in this region, R larger than capital R, which doesn't contain the position of my point charge, the divergence of this one is 0. The divergence of this one is also 0. So the divergence of the electric field is equal to 0 if R is not equal to capital R. Because if R is less than capital R, I know that the electric field is 0 anyway. But if it is 0, then its divergence is also 0. If R is larger than capital R, then this is my electric field, and the divergence of that term is always 0. Or if you want to calculate it explicitly, the electric field, if you look at the expression of the divergence in spherical coordinates, this is 1 over r squared, del over del r squared times the radial component of the electric field. Well, the electric field only has a radial component, so there are no other terms. If you look at over here, the radial component is proportional to 1 over r squared. If you multiply with r squared, it's just a constant. Derivative just gives you 0. Of course, this is true as long as small r is larger than capital R, because we know that the divergence of this field is proportional to Dirac delta R. So at least we know that there are no volume charge densities, because the divergence of the electric field is 0, almost everywhere except on this surface. Now, it is possible that we have some surface charge density on this surface. Now, let's determine that surface charge density. Now, that surface is this one. It's a sphere. Let me choose my n vector to be the radial vector. Now, I will use this relation over here. This one. Now, since this is my n vector, the top is this region over here, the top of my surface. So as I approach this point from this region, the electric field at the top is equal to q over 4 pi epsilon 0, q over r squared in the r hat direction. This is the top. Because in this region, small r is larger than capital R, So in that region, that is my electric field. Well, of course, at this point, this is capital R, not small r, because I'm looking at this point over here. I'm looking at the electric field at this point if I approach that point from this side, and the electric field at that point if I approach it from below. Well, the electric field from below is 0, because you see if R is less than capital R, the electric field is always 0. So here at these points R is less than capital R, so the electric field is always 0. So E bottom is equal to 0. Oops. Now if I take this difference, E top minus E bottom, I obtain Q over 4 pi epsilon 0, Q over R squared in the radial direction. This is the left-hand side. Well, the right-hand side tells me that it is sigma R, sigma at that point, divided by epsilon 0, and the normal direction is nothing but the radial direction. So I have these two vectors that are equal, so their components have to be equal, or you can just multiply both sides by r hat. You cannot divide both sides by r hat. It's not allowed. But you can multiply both sides by r hat. And that would just give you, this is 1, sigma of r is equal to Q over 4 pi r squared. Well, 4 pi r squared is nothing but the total surface area. So here we have a spherical shell. On the surface, there is a total charge Q uniformly distributed because this expression is independent of where I am on the surface. Everywhere I have the same surface charge density. So these are the basic steps. You calculate the divergence of the electric field. In fact, if you would do it properly, even at small r is equal to capital R, by just taking the divergence, you could obtain the surface charge density. But usually it amounts to, let's say, writing the electric field in this form, taking the derivatives of step functions, etc. So most of the time, you'll kind of avoid the points where the electric field is discontinuous when you are evaluating the divergence. And if you avoid those points, we know that at this point, the electric field is discontinuous. If we avoid that region, the divergence of the electric field is 0. So you can just find by directly substituting these expressions into the definition of the divergence. And once you see that there are no volume charge density, at least in this problem, in some other problem you might have volume charge densities. If you have once you determine the volume charge density, you can look at to see if there are any discontinuities in your electric field. So for example, in this example, there is a discontinuity at r is equal to capital R, and then you look for some surface charge density at that point by just using this relation that we obtained using Gauss law. Let's do one more example in which we will have both a volume charge density and a surface charge density. Let us assume that the electric field, now this is similar to the problem in the book that you have in your homework. Let's say it is equal to Q over 4 pi epsilon 0 times R over R cubed in the R hat if R is less than R, and it is Q over 4 pi epsilon 0, 1 over R squared, again in the radial direction if R is larger than R. Now, this was the example in your homework. Well, here there's no discontinuity in the electric field. So the only possible, at least in this region, this expression is continuous. There's no discontinuity here. In this region, this expression is continuous. There is no discontinuity there. The only possible discontinuity would have been when R is equal to capital R. But if you take the limit R is equal to capital R here and here, you get the same result. So there's no discontinuity. Let's change the problem a bit. Let me say this is Q over 2. Now, the previous example was just as a sphere of radius r, which has a total charge q uniformly distributed over the volume. Now I have modified it. It's no longer a sphere of radius r that has a uniformly distributed charge q over its volume. This is no longer that case. Let's see what is the corresponding charge distribution. Now let's look at the divergence of the electric first of all. This will give me the volume charge density. Well, this expression, it is 0. So the divergence of the electric field is 0 if r is larger than r. This is the point charge, the electric field of a point charge, which is non-zero only at r is equal to 0, which is not in this region. So in this region, the divergence of this electric field is always 0. So there's no charge in that region. When r is larger than capital R, there are no charges. Outside of the sphere, there are no charges. Inside this sphere, well, the electric field only has the radial component, and the divergence of the electric field would be just this expression. And if you calculate this expression, this just turns out to be 3 q over 2 divided by 4 pi epsilon 0 r cubed. Well, I have a linear r dependence over there. Multiplying by r squared, it makes r cubed. If I take the derivative, that gives me 3r squared. R squares cancel. That is the origin of that 3 over there. And this is rho over epsilon 0. So we see that there is a volume charge density inside my sphere. Outside it is 0. But inside, the volume charge density is just q over 2 divided by 4 pi over 3 r cubed. Well, 4 pi over 3 r cubed is nothing but the volume of my sphere. This is just the constant. So inside my sphere, the charge is uniformly distributed. And there is a total charge q over 2 inside my sphere, uniformly distributed over all of the volume. It's just q over 2. Now let's look at if there is any surface charges. Now there is a point. At this point, when small r is equal to capital R, the limit of this electric field and the limit of this electric field, they are different. And since they are different, there should be a surface charge density there. Because we know that any discontinuity in the electric field will be created by some kind of a surface charge density. There's no other way to create a discontinuity in the electric field. Well, again, let's just take our sphere. This is our, let's say, the normal vector. We can take it to be the radial direction. It is perpendicular to the surface. So it basically defines what is our top, what is our bottom. So the electric field at the top would be, well, we will be approaching this point from this region, but when small r is larger than capital R, that is what the electric field is. So in the limit that we reach this point, this will be q over 4 pi epsilon 0, 1 over r squared in the radial direction. Now the electric field at the bottom well, the bottom is where this normal vector starts. So it's in this region is the bottom of my surface. So I will approach that point from the bottom. But that is when small r is less than capital R. In the above expression, I take the limit that small r goes to capital R. And so we see that the electric field at the bottom of the surface is just q over 2 divided by 4 pi epsilon 0, 1 over r squared in the r hat direction. Well, they're almost the same. The only difference being here I have a q, here I have a q over 2. That is the origin of the discontinuity in the electric field. Well, E top minus E bottom, this will be equal to q over 2 divided by 4 pi epsilon 0, 1 over r squared, r hat, which is supposed to be sigma at that point, the surface charge density at that point, divided by epsilon 0 in the r hat direction. So the surface charge density is just q over 2 divided by 4 pi r squared. So essentially my sphere has a total charge q. Half of it is uniformly distributed on the surface, and the other half is uniformly distributed over the volume. So you see here is the half distributed in the volume. Here is the other half distributed over the surface. 4 pi r squared is nothing but the total surface area. Well, you see, rho of r will be equal to q over 2 divided by 4 pi over 3 r cubed. Then I have a step function. The volume charge density is only in the sphere, plus q over 2 divided by 4 pi r squared Dirac delta r minus small r. Here, this is the surface charge density. This is, if you integrate this one over the surface, you get the total charge. Here is the volume charge density. And if you integrate this volume charge density over the volume, over a given volume, then you obtain the total charge. Of course, you can imagine a surface inside the volume, but this Dirac delta tells us that this coefficient over here is kind of the surface charge density. Basically, they carry the same information. A surface charge density, you can write it in terms of a volume charge density using the Dirac delta functions.
Hocam şu batımdaki elektrik fiildi niye eşit olarak yazmadık? R bölü R küp.
Well, you see, the top and the bottom are the top and the bottom of the surface. So we are looking at the electric field not at an arbitrary point, at this point. We are taking the limit from the bottom or from the top, but eventually we are at this point. Now this point has small r equal to capital R. So when I have small r over r squared, r cubed, but small r is equal to capital R, well, let me write it in this form. Because the electric field at the bottom, as your friend pointed out, this is the electric field at the bottom of my surface. It is small r over r cubed. But on the surface, small r is equal to capital R. So they cancel, and I am left with 1 over r squared.
Step fonksiyonuna gerek var. Itibar iddiatıyla zaten R'nin büyük R olmadığı her yer sıkıntı.
But you see, in this problem, we have a volume charge, a charge uniformly distributed over the volume, plus a surface charge. We have both of them. So you see, this is the charge uniformly distributed over the volume of my sphere. This is the charge uniformly distributed over the surface of my sphere. Other questions? No, that's enough if you just write this is the charge density when r is less than capital R, and this is the surface charge density. If you just say these two things, that's enough. What was it? Well, you see, just like most of the time you forget most of the things that you have learned in a class the day of the final, I forget everything about the homeworks the moment I upload them. So I have no idea what the question 4C is. Is it this R plus, R minus stuff? Well, I mean, if you want, we can do it in the recitation, but not today, on Wednesday. On Wednesday, we can discuss in more detail the homework questions. I mean, in that problem, it's just, the basic idea is exactly the same. It can be just a bit more tedious computation. You will see that if you take the divergence, it is zero almost everywhere. There is a singular point when cosine theta was equal to 0, and r is equal to d. That's a singular point. And you have to be a bit careful there. And if you pay a bit attention, you will see that there's a point charge there. Plus, there is a discontinuity at theta is equal to pi over 2. Because on one side, the electric field is 0. The other side, it won't be 0. Since it's discontinuous, then there should be a surface charge density. And the way to calculate the surface charge density is exactly this one. It's just one computation. Other questions? Okay, so work and energy. So what do you remember about work? What is work? How do you calculate the work? So if there is a force acting on an object, and if the object moves from point A to B, if you calculate the total work done on the object by this force F, this is what we call the work done by F on the object. You remember this? Do you all agree? So if F is constant, we can also write it as F dot the position of the point B minus the position of the point A. It takes a simple form. This is the total displacement of the object multiplied by the constant force F. Now, one interesting thing is that if F is constant, the work done is independent of how you go from point A to point B. I mean, this final result is independent of it. So you can just take a straight path or make many turns, curls, etc., curves, and eventually reach the point B. The work done will be exactly the same. So such forces we call conservative forces. And in general, if the work done by a constant, by a force, by an arbitrary force is 0, if you start from a given point and end it at the same point, then we say that F is a conservative force. Well, what we mean by a conservative force is mainly, for example, gravitational force is constant at this close to the surface of the Earth. So since it's a constant, it satisfies this property. And since it satisfies this property, the gravitational force is a conservative force. So we define some kind of a potential energy for gravitational force. And so when I lift this thing up, well, there are many forces acting on it. I am exerting a force on this object. Gravity is exerting a force on this object. But if you calculate the work that I have done on this object, we say that, okay, I have done some work, and that work is stored in the potential energy of my system, in the gravitational potential energy. So there is a work done which stores energy in the gravitational potential energy of the system, and if I just release my hand, I can get back this potential energy, and it will be converted into the kinetic energy, which I can use to do some work, etc. So if you have a conservative force, you can use it to store energy. Well, this should look familiar already from the last week's course, last week's discussion. Well, if we had put one more line over here, that's the electric field. Or considering the electric force, F is equal to Q times E. And if you calculate the F dot dl, the work done by the electric field, this will be equal to Q E dot dl. But this is Q curl of E times dA, which is 0. So the electric force acting on any charge is in fact a conservative force. So you can use this electric force to store energy in a given system. So if I, just like when I lift this thing up, I am storing energy, potential energy, in my gravitational potential energy. If I bring charges from infinity, or if I move charges from one point to the other point, I will be storing some potential energy in my system. And, well, how we define the potential for a conservative force, U was equal to U at the point R, let's say, from some reference point, which we denoted by O, up to the point R. Well, you see, the energy stored in a given system is the work that I have done, not the work that that force has done. It's the work that I have done. But if I'm just storing energy in the potential energy and not in the kinetic energy, so I should keep the kinetic energy constant. Well, to keep the kinetic energy constant, the object shouldn't be accelerating. If it is not accelerating, the total force should be 0. There is the conservative force is exerting, in this case, the gravity is exerting a force in the downward direction. I should exert exactly the same force in the opposite direction with a minus F. So that's why we have this minus in the definition of the potential energy. Because this minus F is the force that I have to exert. F is the force that the conservative force is exerting on my object. And minus F is the force that I have to exert on the object in order to move it from the point O to R. This is equal to minus, for the electric force at least, Q times E dot dl. But this is equal to minus, or without the minus, Q times the integral of E dot dl. But this is nothing but the potential at the point R. You see, the left-hand side is the potential energy. U is the potential energy. That is the potential energy of our system if I put a charge Q at the point R. And V of R is the potential. There's no energy. V is just the potential. U is the potential energy. They even have different units. The units differ by Coulomb. So potential and potential energy, they are completely different things, but they are of course related. Again, keep in mind that here we are assuming that we have these main charges somewhere, which create a potential at this point. And then I am bringing this additional charge Q to that point, that final point. And by bringing it from infinity to that point, y infinity, we are assuming that the potential at infinity is 0. So we are bringing this charge Q from infinity to this point R. And by doing this action, we are storing an energy U of R equal to Q times V of R in the system. Okay, another difference between the potential energy and the potential is that given a charge distribution, it creates a potential at a point. So the potential is a property of the point that you are studying the potential, created by other charges in your system. Potential energy, on the other hand, is a property of all of your system. So when, for example, when we are talking about gravitational potential energy, most of the time we say that it's the gravitational potential energy of this keyboard, but that's a wrong usage. It's the gravitational potential energy of the keyboard plus the Earth system. It's not the potential energy of the keyboard only. But in the case of, let's say, the keyboard and the Earth, of course, since when this is falling down, Earth doesn't really move, so nothing seems to be changing on Earth, so we say that it's the potential energy of the keyboard. But for the charges, we will be making this distinction more emphasized, let's say. The potential energy is a property of the system as a whole. You cannot say the potential energy of part of a system. You can talk about how much the potential energy changes when you bring the charge Q from infinity to its final position. It is given by this expression over here, but nevertheless, the potential is always a property of the whole system, not just part of it. Now, so we can talk about, for example, the potential given several charges, not just one. We can talk about the total potential energy of this system. Well, the total potential energy of this system would be nothing but the work that we have to do in order to bring all these charges from infinity to their final position. So let's say this is charge Q1, Q2, and Qi, etc. So if we release the system, if they're all positively charged, for example, if we release the system, if we let the charges free, then the charges will speed away from each other, converting this potential energy into kinetic energy. So how can we calculate the total work done to bring the system to this final configuration? Well, we can do it by one. Let's bring the charge Q1 first. How much work do we need to do to bring the charge Q1 to its final position? That is our first charge. 0. There are no other charges. Since there are no other charges, we don't need to exert any force on it. So the U is 0. We start with 0. We brought charge Q1. Or let's say 0 times Q1. We bring it to its final position. The potential at that position is 0. So the change in the potential energy of the system will be its charge multiplied by the potential at its final position. Then we bring the second charge, Q2. So what will be the work that we have to do in order to bring the charge Q2 to its final position? Let's call the position of Qi to be Ri. Well, we already have the charge Q1 somewhere. So the work that we have to do, the additional work that we have to do is Q2 times Q1 over R1 minus R2. Why? Because we have Q1, which is creating a potential now. And at the position of R2, the potential created by this Q1 is Q1 times R1 minus R2. You see, look at this expression over here. Now, V is the potential at the point R created by other charges in the system, not by Q, but the other charges that are already existing in the system. I brought Q1, it is sitting over here at the position R1. Then I'm bringing R2 over here. But at this point, this charge is already creating some potential. And the potential of a point charge, sorry, I forgot this 1 over 4 pi epsilon zeros. This charge Q1 creates a potential at this point, which is 1 over 4 pi epsilon 0, Q1 over this distance. And the energy additional energy stored in my system by bringing this Q2 charge over here is nothing but Q2 times the potential created by the other charges in my system. Now I have this Q1 charge over here and Q2 charge over here. And I bring Q3. Well, at this point, both Q1 and Q2, they are creating a potential. Plus Q3. Now the potential at the position of Q3 is created by Q1 and Q2, and that will be the Q1 creates the potential R3 minus R1, 1 over 4 pi epsilon 0, and Q2 creates the potential Q2 over R2 minus R1, 1 over 4 pi epsilon 0. And I keep going, keep continuing bringing the charges one by one. So eventually, I will be bringing the charge Qi. I should multiply Qi by the potential created by all the other charges that I had already brought. And they, each one, let's say the charge Qj, will be creating a potential Qj over its distance from the position of Qi. We have this 1 over 4 pi epsilon 0 summed over all j from 1 to I minus 1, because we are just summing over all the charges that we had already brought. We brought the Q1, Q2, Q3 up to Qi minus 1, and then finally we are bringing the Qi charge. This is the work that we have to do. Plus, you just have to bring all your charges one by one. Which, if you want, you can just write it as U is equal to, let's say, sum over I, Qi times Vi, where Vi is the potential created by the charges Q1, Q2, up to Qi minus 1. Now this will be just a shorthand notation. And if you like, you can also write this Vi explicitly over I, Qi, sum over j from 1 to I minus 1, Qj over Ri minus Rj times 1 over 4 pi epsilon 0. This is the potential energy stored in the configuration, in the charge configuration I have. In principle, I can extract this energy from my system.
Hocam şu yukarıdan Qi toplam bir şeyler yapıyor. Bu sadece bir tane yükü şu sistemin içine sokmak için yaptığımız bir şey.
This one, no. Not putting one charge into this system. What I'm imagining here is I brought the charge Q1, then the charge Q2, then the charge Q3, Q4, Q5, Q6, up to Qi minus 1. I brought I minus 1 charges into my system. I'm forming this configuration. I brought not all of the charges, but only I minus 1 of them. Then I'm bringing the charge Qi, the ith charge. I'm bringing the ith charge where I already have I minus 1 charges in my system. And eventually, if I have n of them, I should be summing I from 1 to n. N being the total number of charges. I will do one more trick here. Let us just, for the simplicity, let's assume we have only 3 charges. Not many of them, but just 3 of them. So we will have few terms. So the total energy of my system will be, well, Q1 times 0 plus Q2 times 1 over 4 pi epsilon 0, Q1 over R1 minus R2, plus Q3 times 1 over 4 pi epsilon 0, Q1 over R1 minus R2, plus 1 over 4 pi epsilon 0, now R1 minus R3, Q2 over R2 minus R3. This is the total potential energy of my system. Let me rewrite it a bit. I will say that this is equal to 1 over 2 Q1 times 1 over 4 pi epsilon 0 Q2 over R1 minus R2 plus 1 over 4 pi epsilon 0 Q3 over R1 minus R2. Well, you see, this term was in fact over here. Now, this term I divided into two parts. Each one will have 1 over 2. So 1/2 of this term is over here, and 1/2 of this term is over here. Plus 1 over 2 Q2 times 1 over 4 pi epsilon 0 Q1 over R1 minus R2 plus 1 over 4 pi epsilon 0 Q3 over R1 minus, no, this is R3. This is R2 minus R1, R2 minus R3. Now, I had this term. Half of it is over here, half of it is over here. So when I sum these two, I obtain this term. Now, this plus this one, you see, they are both proportional to Q3. One is multiplied by Q1, the other one is multiplied by Q2. This plus this one is nothing but half of this term over here. So I also need to add the half of that one. Q3, 1 over 4 pi epsilon 0, Q1 over R3 minus R1, plus 1 over 4 pi epsilon 0, Q2 over R3 minus R2. Well, I only rearrange the terms a bit. If you just sum all, here there are like 1, 2, 3, 4, 5, 6 terms, but each term has a pair, so if you just sum them up, you end up having 3 non-zero terms. Thanks to these factors of 1 over 2, when you sum all these terms, you obtain the above line. But let's look at these terms one by one. Here I have Q1 times these two terms, but these are, okay, this is the potential created at the position of Q1, created by the charge Q2. This is the potential, contribution to the potential, at the position R1, created by the charge Q3. So this sum, these two terms, are nothing but the potentials created at the position of Q1 by the other charges in my system. So you see, before, when we were making this sum over here, VI was the potential created by the charges that I had previously brought to my system. But in this expression over here, this is the potential created by all the other charges. Here I'm not really considering bringing them one by one, but nevertheless it is equal to that expression that I obtained when I brought them one by one. This expression is just you multiply the charge with the potential created at the position of the charge due to all the other charges and sum them up. So this is equal to 1 over 2 Qi, let me call it Vi prime at the position Ri, where Vi prime is the potential created by all other charges. In the system. So you see this expression, 1 over 2 Qi Vi prime for the total electrostatic potential energy stored in the system, looks very similar to this expression over here, except then that factor 1 over 2. And the reason for that 1 over 2 is that here VI is the potential created by the charges that I brought first. It doesn't contain the potential created by the charges that I will bring later on. Whereas this one over here, VI prime, is the potential created by all the other charges in my system. So that's the difference between these two expressions. They are equal to each other. Any questions?
Hocam elektrik alanında teker teker bütün yüklerle uğraşmamamız için gradient almıştık ya tavsiye. Burada da bir var mı?
Well, we will express this in terms of the electric field in the next hour.
Hocam şimdi hani in the system dedik ya, burada bir sistem, burada başka bir sistem olsa yükle tam bu ikisinin ortasında olur.
You see, here we are summing over all the charges, not just one of them. So this is, yeah, this is the potential. You see, you can bring more than one system together. So you have one system over here. You can talk about the potential energy stored in this system. You can have the other system over here. You can have the potential energy stored in this system. And then well, in these potential energies, to calculate them using this sum, you just multiply each charge by the potential created in this system, by the potential created by the other charges in this system. You can calculate the potential energy of this system only. You can also calculate the potential energy of this system only. But then there's also the potential energy of bringing these two systems together. So let's give a 10-minute break, and then we will continue.